We probably gradually start. Um, to, Today we have a pleasure of having Jean-Marc Luck. His name is not written here, but
no, because it's my name.
Yeah. Usually it's
It's
anyway
right.
from Saclay to speak about maximal entropy random walk. As far as I understand, not on quantum mechanics, but on random systems, nevertheless.
Yes, thank you. And thank you for the invitation. It's always a pleasure for me to return to this very pleasant place. So the subject I chose today is on maximal entropy random walk, and it's. Do I have to switch on? Or the audience is. The audience is. Is it okay? Is this okay?
Yes, it's on.
It's on? Okay. Yes, so this talk is based on some recent work I did with a Polish team from Krakow around Zdzisław Burda, and the preprint was posted last month on the archive. So it's not in the mainstream of my activities because I'm mostly active in non-equilibrium statistical physics of classical systems. But I'm also interested in stochastic processes, so there is some bridge with the subject I'd like to present today. So let me start with the setup of this talk. First, a brief motivation. Why a new definition of of random walk in 2008? It's a very old object and quite extensively studied. Then I'll provide a brief reminder of what we call ordinary random walk, namely usual random walk on a graph. Then I'll define what we call the maximal entropy random walk, and then I compare both models using several examples. First, on small graphs or on ordered structures like a 1D or a 2D lattice, and the last part will be on disordered systems, where you see that the maximal entropy random walk is very different from the standard one. So let me start with some motivation. One can give many kinds of motivation in studying random walk. I'm giving some lines of thought around along the lines who brought my Polish colleagues to consider this model. So it's the motivation from the viewpoint of people doing high energy physics, actually doing quantum field theory. So the general framework is how to discretize path integrals in quantum field theory, or how can use sum of random trajectories. Well, it's known that one can use periodic lattices, put field theory on a lattice, and it's known for long that it's convenient to do Monte Carlo simulation, and the prototypical example is certainly lattice gauge theory. But there are also there have been several attempts to use random geometric structures to discretize space-time to be used in quantum field theory. The first attempt is probably the calculus by Regge, who proposed, so it dates back to 1961, who proposed to use discretization of space to implement the equation, the Einstein equations for classical gravity. Another important milestone along this line of thought is the proposal to use random lattices in numerical simulations in some field theories as an alternative to regular ones. And this was put forward by Christ, Friedberg, and Lee in the 80s. And another subject which is related to random geometry is what is now called 2D quantum gravity. After 't Hooft. 't Hooft didn't use didn't have in mind this application to quantum gravity, but he realized that random surfaces can be thought of as duals to graphs in matrix field theories, and it has expanded to this whole subject of quantum gravity. So our modest approach along this line of thought is to find a novel principle to define discretized path integrals, namely maximal entropy, and to show that it works at least in the very simple case of a random walk. So let me start with a reminder of what I call ordinary random walk. So for me, space will be discrete. It will be a graph or a lattice or network, and time will also be discrete. So I consider an arbitrary graph like this one. And I attach to it an adjacency matrix. It's probably well known to most of you, A. And the entries Aij are 1 if the nodes I and j are connected, are neighbors on the graph, and 0 else. My graph is reasonable, namely there are no multiple bonds between any 2 points, and there are no tadpoles as well, no links connected a node to itself. So Aij is really 1 if 2 different nodes are connected. And the degree or the coordination number of site I is just the sum of Aij over j. I denoted by Ki. So what is ordinary random walk on such a graph in discrete time? Well, it's a stochastic process. So it's a Markov chain, and the transition probabilities from I to j is just given by Aij. So it's non-zero only if the 2 nodes are connected, and it's given by 1 over Ki. So it means that if you are at site I, you have K sub I neighbors, and you jump to one of them with equal probabilities. That's what this formula says for you. Pij is 1 over the degree of I, if I and j are neighbors. These are clearly normalized by definition of the degree. And the time-dependent occupancy probabilities, Pi of t, probability of being at site I at time t, obey this simple recursion equation between times t and t plus 1, because time is discrete. And if you look for the long time behavior of this equation, you find the stationary occupancy probabilities, which are just, so pi I star reminding that it's stationary, and they are just proportional to the degrees. So the probability, the stationary probability of being at site I is proportional to the degree K sub I, and the rest is just a normalization.
What is occupancy probability?
Oh, it is the probability of being there, of occupying site I. So it's the occupancy probability of site I in the stationary state. You have a finite graph, so there is a unique stationary measure that you reach exponentially. For the time being, I'm on a finite graph. Yes.
Okay.
Yeah. You will see examples where there are results on infinite lattices or so. But for the time being, to be simple, I'm on a finite graph. Okay. So here are the stationary occupancy probabilities, and I'm interested in something which is less well known, maybe, which is what I call path statistics. I take a t-step path, gamma sub t, which joins nodes I0 to I1 and so on to I sub t, and I'm asking what's the probability of having this t-step path. So it is just, I assume that I0, I1 and so on form a connected path on the lattice, so all the A matrix elements are 1, so the P's are just P I0, I1 and so on, and they are just so, oh yeah, I got this laser. So the probability of a given t-step path is just 1 over the product of the degrees of the visited sites in this ordinary random walk. So what can be said? As soon as the graph is not regular, so the degrees are not constant, then this probability depends on the whole path and not only on the endpoints. Another way to put it is that not all paths are equivalent. And more precisely, paths visiting low-degree nodes are more favored. Because you see, you have a larger weight if the degrees are smaller. So that's a property of ordinary random walk that is maybe not so well known, and that's essentially, this observation is the starting point of what we were doing. So, how to characterize these non-uniform probabilities among these paths? Well, a way of characterizing that is to compute the entropy, because it will provide a quantitative measure of this effect. So let's see how this works. I consider two fixed endpoints, I0 and IT, and I consider the entropy of all t-step paths going from I0 to IT. So it's just given by some p log p, where the gamma t's are all these paths, and it's a general result on Markov chains. Just open standard references on Markov chains, that this entropy grows linearly with time, with a number of steps. It's essentially physically obvious. And the rate, namely the limit of s of t divided by t, small s, the entropy creation rate, is given by this double sum, where you have the stationary occupations and the transition probabilities, the hopping rate. It's a standard result. It goes back at least to the 1950s. And here this O is there to remind that we work for ordinary random walk. So here we use the previous expressions, and we find that this entropy rate is sum of k log k of sum of k. So it's just explicit expression in terms of the degrees of all the nodes. So mentioning infinite, going to the limit of an infinite graph, if there is a well-defined thermodynamical limit, then the entropy rate is just the mean of k log k over the mean of k. So it has a well-defined limit for an infinite system. So this is for the entropy of ordinary random walk. And now I'll try to compare it with the maximal possible entropy. So what is the maximal possible entropy for a random walk? Well, it corresponds to all t-step paths being equally probable, by definition of an ensemble with maximal entropy. So again, I consider two fixed endpoints, I0, IT, and I assume that all t-step paths are equally probable. For the time being, I will compute the corresponding entropy, and then I will show you that there is a way to realize this, to realize that all paths are equally probable, and that's what we call the maximal entropy random walk. I will give the explicit construction later on. For the time being, I just evaluate the entropy. So this maximal entropy, S sub m, as opposed to S sub O, is just the log of the number of such paths, because they are equally probable. And the number of such paths is just the tth power of the adjacency matrix between the two endpoints. Because by definition, the adjacency matrix counts one per step, and matrix products correspond to concatenation of steps. So it's the log, and here I put the asymptotic expression of this matrix element for large T, lambda to the T times psi I0 psi IT, where lambda is the largest eigenvalue of the adjacency matrix, and it's the Perron-Frobenius eigenvalue, so it's real, positive, non-degenerate, and so on. And the corresponding eigenvector psi is of constant sign, say that it's positive and normalized. So I have this asymptotic expression, hence the entropy rate log of lambda. So if I have the maximal entropy rate is log of the largest eigenvalue of the adjacency matrix. So we have lambda is e to the maximal entropy is larger than or equal to, a priori, to the exponential of the ordinary entropy. And both lambda and the exponential of the ordinary entropy can be interpreted as the effective degree of the graph. Because if the graph is regular, all sides have the same degree, then of course I get e to the s0 is k, because you remember, yeah? If k is a constant, then e to the s0 is k, and I also get e to the sm is lambda, and it's also k. So both can be interpreted as the effective degree of the graph. So as I will use this formula later and show you more numerical values and so on, maybe it's better that I write it on the board. So lambda is e to the sm larger than or equal to the e to the s0. Both sides can be interpreted as the effective degree of the graph. Lambda is the Perron-Frobenius eigenvalue, and S0 is the entropy rate of the ordinary random walk. So if I go back to the graph which was used initially as an illustration, this one, on this one I can evaluate the two quantities and I get this. Well, it has 11 nodes, but the characteristic polynomial can be factored. So this lambda is only of degree 6, and it has this value, 3.291, whereas the exponential of the ordinary random walk entropy is this combination of numbers, and it's 3.18. So you see they differ by a small amount, and they of course obey the correct inequality. And both can be said to be the effective degree of the graph, which is actually it's in the right. If you take the mean degree as the third possible definition, if you take the mean degree, you get 3.09. It's 3 plus 1 over 11. So 3.09, 3.18, 3.29. So they are all in the same ballpark, but they all have different definitions and obey well-defined inequalities. So this is for the evaluation of this maximal entropy. Yes, as a byproduct, I emphasize this inequality. If I take the log of these quantities, this involves pure concepts of graph theory. You have the degrees of the sides, and you have the largest eigenvalue of the adjacency matrix. And we have not been able to trace this in the literature. The inequality is often, first, it's true. Second, it's often the difference between both sides is often very, very tiny. You will see more examples later. And we've not been able to trace it. I mean, there are entire chapters of books with inequalities on the Perron-Frobenius eigenvalue of the Laplacian on the graph or of the adjacency matrix on the graph, but we found nothing similar. You will see that there are cases where it is saturated. I'll give you such examples. So far so good for the entropy, and now can one construct by local rules a random walk which indeed realizes this maximal entropy? And the answer is yes, and that's our main construction. So the goal is to construct a simple Markov process having this maximal entropy rate, log lambda. And the tool, if lambda has to play a role in the game, then one has to start in some sense with the Perron-Frobenius, with the adjacency matrix and its eigenvalues and eigenvectors. So I consider the eigenvector psi and the associated eigenvalue lambda, which have already been used before in the calculation of the entropy. So they obey this by definition. And as I told you, the psi's are positive, and they are normalized in this way. So the recipe is rather simple. You need something which is normalized. So this is the classical normalization of the hopping rates, and this is, if you wish, a quantum equality on the eigenvector. So you essentially identify both. So you see, the construction is not very involved from this viewpoint. So you use these transition probabilities.
So use transition probabilities
Build
eigenvectors
of the eigenvalue and the components of the eigenvector of the transition matrix. But once the structure is known, once the graph is known, you compute this, and you have the transition probabilities, which are positive, normalized. And
Is it obvious that it satisfies this maximal entropy?
I will tell you. Yes, it's essentially obvious.
Okay.
It's essentially obvious. So this is the construction. So first, the hopping rates are normalized. Second, so these are results which can be checked by elementary means. The basic properties of this maximal entropy random walk. First, the stationary occupancy probabilities, psi I star, are just the square of the wave function. So from now on, I use the name of wave function for this maximal eigenvector, this Perron-Frobenius eigenvector. You see, so this classical quantum correspondence shows up in this very appealing way, say. If I now go back through the evaluation of the path statistics, you remember the entropy of t-step paths. Well, the probability of observing a path gamma t is given by this, so it only depends on the endpoint. And it's 1 of the lambda to the t. Yes? Because essentially the Pij depends on the ratio psi j to psi I. So if I evaluate the probability, the weight of a whole path, I have a product of such probabilities. So of course, if the path exists on the network, is connected, all these a's are 1. I have 1 over lambda per bond, per step, and these ratios cancel out to give this. So the probability of a given path only depends on the endpoints. That's the novel property with respect to ordinary random walk. All paths are equivalent at fixed endpoints, and of course the entropy is maximal.
This value of psi I, is it larger on the sides with larger degree or smaller?
You will see examples. I mean, all the rest of the time will be devoted to more and to examples. It's large. It's larger if you have a larger degree. But what is more interesting is what happens if you have a randomly disordered structure. Where will it be large? That's what will come now. So what about dynamics, transport, and so on? And instead of giving general results, I will show you examples. So the rest of the talk is devoted to examples on which more and more complex, on which I will compare ordinary and maximal entropy random walks. So let's start with a zero-dimensional toy example. So I take this. Yeah, you take a square, you make one diagonal. So two nodes A and B have degree 3, and C and D have degree 2. So nothing can be simpler. For ordinary random walk, these pi's should be pi stars, actually. From now on, all the pi's are the stationary values, so they are pi stars. On A and B, I have 3 tens, because they are proportional to the degrees. And on C and D, I have 2 tens. And the exponential of the entropy rate is this number. Now, if I go to maximal entropy random walk, I evaluate the Perron-Frobenius eigenvalue. I get this number involving square root of 17. So the eigenvector also involves square root of 17. And here are the stationary occupation probabilities. So of course, they are symmetrically displaced with respect to a quarter. And here are the numerical values. So you see, here, the 2 nodes with higher degree they already have a higher probability in ordinary random walk, and this effect is slightly emphasized for maximal entropy random walk. As far as the difference between lambda as e to the s0 is concerned, it's very tiny, you see, 2.56, 2.55. So the general rule of thumb from this toy example, and even from the previous one, is that if you have a finite graph and practice a small graph, there are only small differences between the two constructions. Of course, the expressions of the numbers are very different, but the numerical values are often very, very close. Okay. Now, I go to the 1D example of an open chain like this. You have an open linear chain with n nodes. N is at least 2. So all the inner nodes have degree 2, and the two endpoints have degree 1, of course. They are special from that viewpoint. So what about ordinary random walk?
Why it's open? It's closed.
So when it's closed, when the chain is closed on a circle,
You
if
mean
you have
closed in this?
Yes, yes, yes. I say open in that sense. Open ends. Yeah. In this context, open means this. It doesn't mean that things are flowing in. No, no, no. It's just this graph. So for ordinary random walk, the stationary occupancy profile is flat within the graph, and it's different at the endpoints by a factor 2. And the entropy creation rate is this number. It's almost log 2, but with a slight size effect. The bulk log 2 is just I have two possibilities at each step, of course. What about maximal entropy random walk? You will see illustrations later of these, but I first give the general formulae. Lambda is 2 cosine pi of n plus 1, and the occupation profile is a sine squared. So it's 0 at the endpoints, and it's maximal in the center. So here are the general formulae of these open linear chains, and you will see that special cases will tell us more. I first start with n equals 2. So if n equals 2, I just get this very simple case. And the formulae show that ordinary and maximal entropy random walk are identical. Well, it's clear because we are facing a regular graph. K is constant. So if K is constant, as I anticipated already, all these quantities are equal to K. So no surprise. N equals 3, like this graph. They are still identical. And there, it's slightly more surprising, but it's a property of maximal entropy random walk that it coincides, it's identical to ordinary random walk on a bipartite structure. A bipartite structure, it means that the vertices of degree k1 and of degree k2 alternate, in the sense that if you are on a site of degree k1, all your neighbors have degree k2 and vice versa.
Is it general property of any bipartite?
Yes. On any regular graph, it's rather obvious.
Yeah, right.
And also on any bipartite graph, ordinary and maximal entropy random walk do coincide. And these are essentially the only generic cases. And these are also the cases where the inequality, of course, is saturated. And generically, these are the only two classes. And on a bipartite graph, lambda is e to the sm, it's also e to the s0, and it's just the square root of the product k1, k2. K1 and k2 just alternate. And that's all, because there are no tripartite graphs in this sense. Because if you have degree k1, your neighbor has degree k2, but you are one of the neighbors of your neighbor. So it cannot, if it closes, it's with period 2, it cannot be larger. Okay, so go to n equals 4, this graph, 2 internal nodes, 2 endpoints, and here they differ finally. Lambda is 1.618, and e to the s0 is 1.587. So tiny but non-zero difference. And again, these two numbers are very different. From an algebraic viewpoint, they are very different, and numerically very close. So now, a plot of the, in order to prepare for the rest, what's the profile of the stationary probabilities in this open chain? I take n equals 29, just to have a large number, but not too large in order for you to see all the points. So, what I want to emphasize here is that this profile is repelled by the endpoints. And more generally, it's repelled by the points which have a lower degree. So, the profile in circles is that corresponding to ordinary random walk. So, as I told you, it is flat within the bulk of the graph, and it drops at the two endpoints. It drops by a factor 2. So, this repulsion effect can be said to be local. It only affects a very small boundary layer near the boundary. To the contrary, this repulsion effect is global for maximal entropy random walk. You have a sine profile for the wave function, so a sine squared profile for the occupancy probabilities. So this is the sine squared profile. So you see that the repulsion by the endpoints affects the whole profile. So that's essentially all what can be learned from this simple 1D example of the open chain. Now I go to a higher dimensional example, just to show you that it also works for higher dimensions. Here, a two-dimensional example. I take a square lattice, so formally infinite, and I add some diagonals to it in order to have two different kinds of nodes. Some have degree 4 and some have degree 8. Or if you look at it at 45 degrees, the black ones form a square lattice, and the lattice is centered. The white ones are in the centers of the square cells. Well, you see what the structure is. And the neighbors are defined by all the bonds, irrespective of their length. So for ordinary random walk, the probability of being onto an 8 is 2 times that of being onto a 4. So again, it's emphasized on larger degrees. And, okay, let me look at this in parallel. For maximal entropy random walk, this is slightly emphasized, just as before. 2.61 instead of 2. The entropy rates are also rather similar. Lambda is 6.47 and e to the s0 is 6.34. And what I want to emphasize here is that if you look at long distance properties, they are also very similar to each other. For instance, if I extract the diffusion coefficient, then these two values are also very, very close to each other, with say a 10% effect. So you see what the diffusion coefficient is, yes? I drop a particle at some site and I look at of course, then the probability distribution, pi of t, will not be stationary, it will spread, and for large times it will spread as a Gaussian packet, and the mean square displacement of this Gaussian packet grows linearly in time, and that's how I extract the diffusion coefficient. Of course, this can be done analytically using a dispersion relation on a lattice. And you see. So, on infinite lattices with no boundaries, I insist on that, there are small differences between ordinary and maximal entropy random walk, including for transport properties. Of course, if I consider an open patch of a lattice, then the story will be different. Yes? Okay. So I guess this closes the part on the ordered examples. So now I go to the, well, for me, most exciting part, where there is an interplay with disordered systems with localization. So that justifies why I'm here. Okay, so I have ample enough time. So now I go to the comparison between ordinary and maximal entropy random walks, but on disordered examples, in the sense of usual sense of the physics of disordered systems. Yeah? Large systems where you have some random distribution of impurities. To be definite, I consider dilution disorder. So I remove a fraction of the bonds of a regular lattice, say a small fraction to control what we do. And I start with a 1D example. So if I take a 1D chain and I remove a fraction of the bonds, then it's disconnected into finite pieces. It's not the case which is the most interested. I mean, this problem can be solved separately on each of the connected components. So to have something interesting, I have to keep a connected structure. So we consider a ladder geometry like this, and only the rungs are diluted. Only the cross pieces are allowed to be absent. So this is a typical configuration. So the vertical rungs or cross pieces are removed with some small probability Q. So we start with observations on the stationary probability density pi I star, which is the square of this wave function psi I. So here I have a plot of the log of the stationary density. As a function of site, there are 500 sites in the site on one of the chains, and this is the vertical bars show defects, namely places where there are no vertical bars here, and this is for 3 different samples of increasing disorder, increasing values of Q. So what can be said on this, and the curves just represent the log, as I said, of the stationary density. So if there are only a few defects, finitely many defects, then we see that the stationary density is repelled by the defects. For instance, look at here, it gets much smaller near the endpoints. And then, again, every successive defect diminishes the value of the wave function.
That log base 2 or 10?
I guess it's natural log.
Natural.
My Polish colleagues prepared these plots, so that's why they are not so, well, there's a lot of information. I would say it's natural log.
They're extremely small then, I mean.
Yes. Here the wave function is 10 to the minus 30 or so. Yeah, it's an extremely large effect. So what can be said qualitatively for the time being, the stationary density is clearly repelled by the defects. And so there is a trend to localization. And where is it maximal? It's maximal in large defect-free regions. So now you start imagining where I'm going. Yeah? Here it's clearly localized in the largest defect-free region. That's the compromise it finds if it's repelled by defects. And so this is the feature which is mostly visible here, also there. There it's less clear to find the largest defect-free region, it's here. And since this workshop is on localization, of course the rest of the wave function has linear slopes here which correspond to exponential localization. So, but since we are we are not living on this logarithmic scale, these numbers are extremely small. What is the most interesting for us, for the properties of maximal entropy random walk, is the regions where this stationary density is appreciable. So how does the analysis go? In this example of the diluted ladder geometry, the Perron-Frobenius, that's not that. The Perron-Frobenius vector obeys this equation, which is probably quite familiar quite well known to all of you. n is the site where you are along one of the sides of the chain, psi sub n, psi n plus 1, psi n minus 1, and epsilon n, which are usually interpreted as the site energies. Here, they follow a binary disorder. I have 1 if the rung is present at site n, and I have 0 if it is absent. And here is the eigenvalue, the Perron-Frobenius eigenvalue I'm looking for. Yes. To derive this, of course, we have used the fact that the Perron-Frobenius vector has maximal symmetry. In particular, it has the same value on both here and there, and so on. Okay. So now comes the key word to understand this phenomenon of localization on the largest defect-free region, that's Lifshitz. Lifshitz is in the 60s has shown what's now referred to as the Lifshitz phenomenon, namely the tails in the spectrum of such a random operator are governed by the Lifshitz states, and the Lifshitz states live on large pure regions. Here, in order to have the maximal eigenvalue, I have to find a long region where all the epsilons are 1. So this is complementary to the observation that locally the stationary probability is larger if the degree is larger. Now, if I want the same to hold in a disordered structure, the degree has to be large, namely epsilon has to be 1, but it has to be large in a large region. That's the novelty which is inherent to the disordered case. So this is the general framework. So now I have to show you how it works in the 1D case, what kind of prediction it leads to, whether they are confirmed, and so on. So in the 1D case, described by this equation, I have to consider to find a pure segment, namely defect-free, so epsilon is 1, for n, say 1 to L, a pure segment of length L. This occurs with probability p to the L, because p is just the probability of having 1 here. So I have to solve this equation on a segment of length L. With what's the boundary conditions? Well, at least in this 1D case, it's known from the systematic study of specific examples that they do not really matter. They only change prefactors. So I can assume Dirichlet boundary conditions. So the wave function vanishes at both endpoints. Of course, it's not strictly true, as we have seen, but this will not change the main results. And here I refer to a review of Theo Nieuwenhuizen on this Lifshitz phenomenon, especially in 1 dimension, which summarizes a lot of common works we did in the 80s of this kind of systems. So if you assume this, then you have a sign profile in this pure segment, and the leading eigenvalue is given accordingly by this formula. So it's 3 minus a correction of order 1 over L squared. And L, well, you will see what L is. So what is the usual interpretation of this result by Lifshitz? For an infinite system, in the thermodynamical limit, it says, well, with some probability p to the L, you have an eigenvalue of order, I just show you these two. The usual argument of Lifshitz goes as follows. With probability p to the L, you have an wave function, an energy which is close to the formal endpoint, to the nominal endpoint, by a quantity 1 over L squared. So if you eliminate L between both estimates, you get the Lifshitz prediction as it's usually presented. Namely, you have an exponentially small vanishing of the density of states near the band edges. So essential singularity in the density of states of this form. the density of states vanishes as e to some negative power of the distance to the endpoint. Why an exponential singularity? Because an eigenstate with this energy lives on a very large defect-free region, and to build this region you have to pay an exponentially large weight, p to the L. So this is the standard Lifshitz phenomenon. In the present context, the situation is slightly different because we have a finite sample of length L, and we want the largest eigenvalue on this finite sample and the corresponding eigenfunction. So, in the present context of 1D, the leading Lifshitz segment has a logarithmic length. I use p to the L is now 1 over this length, because it's just the probability to have one such event in my sample of length L. So I can allow probabilities of order 1 over my length L. Whence this estimate? The largest defect-free segment grows, the size grows like log L over log P. And the Perron-Frobenius eigenvalue, my lambda, which I'm using from the beginning, it scales accordingly. Namely, 3 minus lambda is 1 over this squared. And this is a plot of numerical values which shows that this indeed works. So this is a plot of 3 minus lambda to the minus 1/2 as a function of log L. Here are the data, and here is the line has the predicted slope, which is pi squared in the right units. So you see that things do work. This quantitative analysis has not been done for the wave functions or for the stationary probabilities. They have just been done at the level of lambda, but I guess it's convincing enough. So I'm now presenting mostly plots of what happens in higher dimensional disordered systems. So here are plots made by my Polish colleagues. So this is a square lattice with bond dilution. So you remove bonds of the square lattice with some small probability, very small here. And the bright dots denote the endpoints of these bonds which have been removed. So here I have removed one bond here and one bond there. And what is plotted in levels of color, of gray color, is just the stationary probability density on these finite samples. I guess it's with periodic boundary conditions, and it's clearly with 4 increasing values of disorder. So what can be said? Well, clearly the stationary density is repelled by defects. Yeah, it's black around the defects, low density around the defects. And if disorder increases, or if you wish, equivalently, if at fixed disorder the sample size increases, you go from a situation where you are repelled by a few defects to this situation where you are repelled by so many defects that you live here right in the middle of the region where you have no defect. So that's the Lifshitz mechanism at work. On large enough samples, there is a Lifshitz phenomenon, and qualitatively it goes like this. The stationary probability density is asymptotically localized. Clearly, if you were presented this kind of plot before the explanation, you would say that this is clearly a localized state. It is localized in a Lifshitz region which is nearly spherical, nearly circular here. I mean, the spot is nearly circular. The volume of the Lifshitz region grows logarithmically, log L over log P, P being the fraction of unaltered bonds with bond dilution, and the Perron-Frobenius eigenvalue scales accordingly, namely the difference to the nominal upper edge of the spectrum, which is here the coordination number of the square lattice, 4, scales as 1 over log L to this power 2 over G. So that's what can be said concerning higher dimensional disordered systems. So I have just a few minutes to present this outline. Well, first to remark that maximal entropy is a universal tool that is used and abused in many, many different areas. Often it leads to rather uncontrolled approximations. Here we have kind of reversed the logics in the sense that we have used it as a principle to define new processes, and this example is just a random walk, so to discretize sums of a path of a free particle. So as I said, it has been implemented as maximal entropy random walk. Among the first results, we have this inequality, which I find intriguing. Well, what I find the most intriguing is that it's not in textbooks on graph theory, because it's a simple looking result in a very classical and well studied area of graphs and spectra of graphs. And going back to physics and to the physics of disordered systems, on irregular graphs, first maximal entropy random walk realizes what it is meant for, namely to give rise to a maximal entropy, which is slightly larger than the entropy for ordinary random walk. It is repelled by boundaries and defects in general. And on disordered systems, in the sense of random disorder, as we all like and love, there are so many boundaries and defects that it leads to a localization, even though it's a purely, of course, a purely classical problem, through the Lifshitz phenomenon. That the probability density of the random walker ends up being localized in a Lifshitz sphere. So I think I'll stop there, and thank you.
Questions, please? I ask one. So you just proposed, this is a nice way to visualize these rare regions, basically. So
Yes.
it just because usually it's not that easy to see where they are. You just develop this random entropy work, and it automatically localizes.
It will find for you the largest Lifshitz
This cavity.
sphere.
This
Yes,
cavity.
and not the second largest.
No,
It will manage to find the largest.
the largest cavity.
Yes, it's a way to, maybe it's a way of using it, yeah. Maybe in image analysis or whatever. If people are interested in the largest void, they leave.
No,
Of course, it's weighted by the fact that it has to be nearly spherical. You know, the Lifshitz argument, all the evaluation relies on a spherical region. And it is known, it's even known rigorously, that the right form of the Lifshitz singularity in the density of states correspond to a spherical region.
I see.
The prefactors and so on, the prefactor, you see, the prefactor which was pi in my case.
Is this in that review that you referred to?
Well, no, it's even older. The prefactor here, in d dimensions, it's known, and it's a zero of the Bessel function in d dimensions, so it relies on the fact that the leading, the Lifshitz spheres are spherical. Here it's slightly different because we are on a finite system. So there is a largest region, and largest means optimal, so nearly spherical and largest. But if people are interested in this kind of void, then they just put a maximal entropy random walker and it will localize there. Yes.